A plane weighing over 400 tons, and it just floats, not for a second, not for a minute, for 14 hours straight at 39,000 feet above the ground. And the crazy part? The engines aren't even what's keeping it up. Most people think it's the engines. Makes sense, right? Big, loud, powerful, they must be doing the heavy lifting. But no, the engines have one job only: push the plane forward. That's it. They don't lift anything. If you turned off the engines mid-flight, the plane wouldn't instantly drop, it would glide. Because what's actually holding it up is something far more invisible. It's air. But not just air sitting there doing nothing. Moving air. And here's where it gets interesting. The wing is shaped in a very specific way. Thicker on top, more curved, flatter on the bottom. When the plane moves forward, air splits around the wing. The air going over the top has to travel a longer distance, so it speeds up. Faster air means lower pressure. The air underneath moves slower, higher pressure. And that pressure difference, that gap between top and bottom, that's what pushes the plane upward. That's lift. But there's a second thing happening at the same time. The wing is angled slightly, what engineers call the angle of attack. As air hits the front of the wing, it gets deflected downward, and Newton's third law does the rest. You push air down, air pushes you up. Every single second of flight, those two forces are working together. Now here's something most people never think about. The four forces of flight are always fighting each other simultaneously. Lift, pushing up weight; gravity, pulling down thrust; pushing forward drag; air resistance, slowing everything down. The plane isn't magically balanced. It's constantly managing all four of these forces at once. The moment any of them gets out of sync, that's when things get dangerous, because none of this works without speed. Zero speed equals zero lift. The wing only starts doing its job once enough air is rushing over it, fast enough to create that pressure difference. Below a certain speed, no matter how big or perfect the wing is, it can't hold the plane up. That's why takeoff is the most physically intense phase of the whole flight. The engines are working at near full power, the plane is at its heaviest, full of fuel, passengers, luggage, and it has to reach somewhere around 160 to 180 miles per hour, 260 to 290 kilometers per hour, before it can even think about leaving the ground. And the runway isn't just a convenience, it's a necessity. It doesn't stay the same shape during flight. It physically transforms. Watch the wing during takeoff from your window seat. You'll see panels sliding out from the back. Those are flaps. They extend backward and downward, making the wing larger and changing its curve. This gives the plane more lift at lower speeds, so it doesn't need to accelerate to insane velocities before it can take off. At the front of the wing, slats extend forward. Their job is to keep the airflow attached smoothly to the wing surface, preventing it from separating and causing what's called a stall, where lift suddenly collapses. A stall near the ground during takeoff or landing is one of the most dangerous situations in aviation. Once the plane climbs and reaches cruising speed, all of those extra elements retract. The wing becomes clean and smooth, optimized for efficiency, not for slow speed lift. Because at cruise, you don't need maximum lift anymore. You need minimum drag. That's not random. At that height, the air is thin. Less air means less resistance against the plane, which means the engines don't have to work as hard to maintain speed. The plane burns significantly less fuel per mile traveled. Temperatures are extremely cold, around minus 60 degrees Fahrenheit, minus 51 degrees Celsius outside, which actually helps jet engines run more efficiently. And turbulence, most weather systems, storms, heavy clouds, wind shear, exist below 30,000 feet. Up at cruise altitude, the air is generally much more stable. That's why your flight is usually smooth once you're up there. But go too high and everything changes. Above 42,000 feet or so, the air becomes too thin to generate enough lift. The engines start struggling to find oxygen to combust fuel efficiently. And if cabin pressurization fails above 25,000 feet, passengers can lose consciousness within minutes from hypoxia, oxygen deprivation. The wing is not rigid, it flexes. During flight, the wingtips on a large commercial aircraft can bend upward by several feet under the load of the aircraft's weight and the aerodynamic forces acting on them. Engineers designed this intentionally. A rigid wing would crack under the stress. Instead, it acts more like a spring, absorbing and distributing forces across its entire length. That flexibility isn't a sign of weakness. It's the only reason the wing survives thousands of takeoffs and landings over the aircraft's lifetimes. At 39,000 feet, a commercial airliner is already traveling close to 600 miles per hour, 960 kilometers per hour. And at that speed, pilots start to feel what engineers call the coffin corner. It's not a metaphor. It's a real defined zone where flying becomes genuinely dangerous from two directions at once. Slow down too much. The wing loses lift and the plane stalls. Speed up too much. And something far stranger happens. Even when a plane is flying at 550 miles per hour, the air flowing over the curved top of the wing is moving faster than the plane itself. At high altitudes and high speeds, that airflow over the wing can actually reach the speed of sound, even though the aircraft as a whole hasn't. When that happens, shock waves form on the wing surface. Not the dramatic supersonic boom you associate with fighter jets, something more subtle and more dangerous. The shockwave disrupts the smooth airflow, creates violent vibrations, and alters how the aircraft responds to the controls. In extreme cases, the plane can start reacting unpredictably, turning slightly when it shouldn't, not responding the way the pilot expects. This is called wave drag, and it's the real reason commercial aircraft have a speed limit, not because the engines can't push harder, but because the air itself starts to fight back. They tried. In the early 2000s, Boeing developed a concept called the Sonic Cruiser, a next-generation aircraft designed to fly significantly faster than any current passenger jet, cutting hours off long-haul routes. The technology was mostly ready, airlines were interested, and then they ran the actual numbers. Aerodynamic drag doesn't increase in a straight line with speed, it curves upward sharply. To add just 100 miles per hour, 160 kilometers per hour of cruise speed, an aircraft might need to burn close to twice as much fuel per hour. The cost per seat mile becomes completely unworkable. Boeing quietly shelved the project. The industry made a choice: carry more people at the same speed rather than fewer people at higher speed. Economics beat physics. When a plane approaches and exceeds the speed of sound, the air molecules in front of it can't get out of the way fast enough. They compress, pile up, and heat up dramatically. The Concorde, the only successful commercial supersonic airliner in history, cruised at Mach 2, roughly 1,350 miles per hour, 2,170 kilometers per hour. At that speed, the nose of the aircraft heated to over 250 degrees Fahrenheit, 120 degrees Celsius. The entire fuselage would expand during flight. The plane would literally become about 10 inches, 25 centimeters, longer between takeoff and landing, then shrink back down as it cooled. Engineers had to design with that thermal expansion built in. Special high-temperature aluminum alloys, carefully engineered gaps in the structure to allow for expansion. Fuel was used as a coolant, circulated through the aircraft to absorb heat from the skin before being burned. And even with all of that, the materials were still being pushed to their limits every single flight. When a plane breaks the sound barrier, it creates a pressure wave, a shock wave, that extends behind it across an enormous distance. When that wave hits the ground, it doesn't sound like a distant rumble. It sounds like an explosion. Windows rattle, car alarms go off, people jump, and it's continuous. Not a single boom as the plane passes overhead, but a sustained shock front, following the plane across the sky. The public reaction was immediate. complaints flooded governments across the US and Europe. Within years, supersonic flight over land was banned in the United States and heavily restricted elsewhere. The Concorde was limited to transatlantic routes only, New York to London, New York to Paris, where the boom could dissipate harmlessly over open ocean. That regulatory wall, not a technical one, is what ultimately killed commercial supersonic aviation. The Concorde flew its last passenger flight in 2003. Right now, a company called Boom Supersonic is developing a new aircraft called Overture, targeting commercial passengers, aiming for Mach 1.7, around 1,300 miles per hour / 2,090 kilometers per hour, with a planned launch in the late 2020s. NASA is actively testing a new experimental aircraft called the X-59, designed specifically to reduce the sonic boom to something closer to a soft thud, quiet enough potentially to fly over populated areas without the old restrictions applying. The engineering goal isn't just speed, it's shaped shockwaves. By designing the entire aircraft, nose, fuselage, wing geometry, to distribute the pressure wave differently, engineers believe they can make supersonic flight acoustically acceptable over land for the first time. If they succeed, the restrictions that killed the Concorde may no longer apply, and that 600 miles per hour limit that commercial aviation has been stuck at for the past 50 years, it might finally start to move.